speaker is going to be Ed Felten. Please welcome.
Thank you. OK, so I'm Ed from the Arbitrum team, and I want to talk about the future of L2 scaling. And I'm going to do this in actually two parts. First of all, I am going to walk through at a high level the mechanisms and the design in the Arbitrum Nitro stack, which is the new stack from our team that is currently on testnet. We will be upgrading our Arbitrum 1 chain to run on this stack. But I think it's worthwhile, before talking about how to scale systems like this up, to deep dive a little bit into how one of them works in a little bit more detail, and to talk about sort of where rollup design is right now, or where it's heading. And then from there, I'll talk a bit about what to do moving forward, and how we can get to the next zillion users. OK, so of course, every talk in this topic is required to start with this slide. This is the famous rollup-centric Ethereum roadmap post from Vitalik. Right? And the point of this is the idea that rollups and the scaling of rollups will be central to the Ethereum rollup scaling story. So let me talk a little bit first about Arbitrum Nitro. First, in case you don't know, we have had a chain out on mainnet since August. There's hundreds of applications there, and if you're interested in seeing examples, you can go to portal.arbitrum.io. Nitro is our new stack currently on testnet, which we'll be upgrading our mainnet to. And I want to talk about sort of the design of this thing in terms of these four concepts. First, it's an optimistic rollup, and I'm going to trust that for this audience, I don't need to explain what that means. So I won't dig into that, but I will dig into the other ones. First, that we separate sequencing followed by deterministic execution. Third, that we put Geth at the core. And fourth, that we separate execution from proving for additional performance. OK, so first, sequencing, then deterministic execution. So let's talk about how a sequencer-based system works. And I think this is pretty typical for what rollups do, but I want to dig into it in some detail to pull out some of the design constraints. So we have a component called the sequencer. It's currently a centralized component, but we'll be migrating it to a distributed system over time. So you have a distributed set of sequencers where you only need to trust that a suitable majority are honest. OK, so the sequencer receives from users some transactions. Users send their transactions. And what the sequencer does is puts those transactions into order and sees that those transactions are recorded on the main chain. Now, the sequencer, an honest sequencer, will sequence all transactions and will do so in a first-come, first-served fashion. A dishonest sequencer might censor you, but there is a backup mechanism that you can use to get your transaction into the sequence and executed no matter what, despite what you might have heard this morning. OK, so the sequencer produces a sequence of transactions in a particular order. That's its only power. That's the only thing it's trusted to do, is put those transactions into order. Of course, the transactions are either signed by EOAs, so the sequencer can't manipulate them, or they come from L1 contracts, and so their call data is recorded on the L1 chain. Either way, the sequencer can't change them. It can only put them into order. That's its job. Now, the sequence transactions are run one by one through a state transition function. This is a fully deterministic function, meaning that what it does is dependent only on the particular transaction that it's currently sequencing, as well as a state. So, and the state, of course, is accumulating changes that have happened over the prior transaction. So the result of your transaction depends only on the genesis state, all of the transactions that have come before it, and the transaction itself, and on nothing else. So the state transition function executes, it updates the state, and it perhaps produces a new L2 block. Those L2 blocks get accumulated. They will eventually be settled back onto the L1 chain. OK, but let's look back at the sequencer. The sequencer first decides within its own head what the order is going to be. Then it needs to tell people. It needs to commit to that. So the first thing the sequencer does is it publishes a sequencer feed. This is something that anyone can subscribe to and receive. It does this very quickly. As soon as the sequencer puts your transaction into the sequence, it will push your transaction out on the feed. So you'll see your transaction out on the feed in less than 1 second. in a typical case. This is the sequencer's promise as to what sequence it will eventually record on chain. But it's important for user experience that this happens faster than L1 finality and even faster than L1 block time, so that users can get a soft guarantee result of their transaction in less than 1 second. So the sequencer publishes this feed, and everyone who is interested can follow it. Now, if you trust that soft guarantee from the sequencer, you know everything you need to know to execute the state transition function, keep your own copy of the state, and asynchronously keep up to date on what the state of the chain is. Right? So as soon as the sequencer publishes your transaction, you know what the result will be if you trust the sequencer's soft guarantee. The sequencer will then later, every few minutes, will take a large batch of these transactions, batching in order to amortize the cost of eventually posting this to L1. Also batching because it wants to compress, and compression will work better if these batches are large. So it'll take maybe a couple hundred kilobytes of transactions, compress them, and then eventually write them back onto the L1 chain. When this happens, and when this L1 transaction to record this has finality on the L1 chain, then you have a hard guarantee of finality of your transactions, because the transaction order is fully committed and the state transition function is fully deterministic, and therefore what the L2 blocks will be cannot be changed. So what this does is it gives you sort of 3 stages of the settling of your transaction. First, there's soft finality, that is finality which is good if the sequencer's soft guarantee of ordering is correct. You can receive that by subscribing to the sequencer feed and then computing the state transition function for yourself. And the guarantee here is that it's correct if the sequencer's feed was correct. That's one reason we're turning the sequencer into a decentralized system, so that you can have more trust in that guarantee. Second, you have full finality. This is the point in time at which the result of your transaction is inevitable. It's known to everyone in the universe except the Ethereum chain. Why does the Ethereum chain not know it? Because the Ethereum chain can't compute along. It doesn't have the compute power to process all of these transactions. That's why we're on L2. Right? So if you want this, you read the compressed batches from the L1, you can decompress them yourself, you can compute the state transition function from over each transaction, and then you wait for L1 finality on the recording of that batch, then you're good to go. So this is basically finality at the speed of L1. And this guarantee is as good as your L1 finality assumption. And then finally, there's a process which on an optimistic rollup takes days, on a ZK would probably take hours, which is for the transaction to be certified to the L1 chain. And this is where the L1 chain knows the result. And that's as a result of that's as a result of the optimistic rollup protocol in our case, or the ZK proof protocol in the case of a ZK. All right, so this is the sequencer piece of it. And there's a few things to note here. The different time constants are really important. The 1 second soft finality is critical for user experience. And you might be a little bit uncomfortable with the soft guarantee. That's why we're moving to a distributed system version of this. Okay, so that is the sequencer piece. All right, let me move on and talk about the next piece of it. This is Geth at the core. And basically, the way that this software stack is built is in 3 layers. At the bottom, we have the core of Geth. Think of the part of Geth that keeps track of the Ethereum state, that emulates the execution of EVM transactions, and sort of that core functionality of Geth. We take that and we use it almost unmodified. We just add a few hooks to it. On top of that, we build this component called ArbOS, not shown to scale. In practice, it's much smaller than the Geth core. And this adds the functionalities that you need to be an L2 chain. This is things like making sure that you can charge for L1 gas, having the necessary support, precompiles, and so on to do deposits and withdrawals, and other functionalities like that. This is everything you need to be a functional L2 chain, which is not already built into Geth. And then on top of that, we have node functionality. If you're going to run a node that can receive RPCs and do all the node things, you need some node functionality. And most of this is, again, code from Geth. Okay, so this is the stack. And this is a significant improvement over our previous stack in that we adopt the Geth core, which gives us excellent compatibility and good performance reliability. This is how the stack is built. Now, the state transition function is basically this orange piece. It is all of the Geth core, and it's also some piece of the ArboEsp. Some of that piece is inside the state transition function, and some of it is doing the various bit jockeying and so on to line things up for execution of the state transition function, which are not part of the state transition function itself. And of course, the node functions, RPCs and all of that, not part of the state transition function. All right, so that's how this maps onto the previous piece of the design. Okay, the last piece is separating execution from proving. And this is, I think, a really cool trick. So here's the previous diagram, the 3 layers in blue, the state transition function outlined in orange. And we do 2 things with this. One thing we do is we take the blue pieces and we compile them to native code. These are all written in Go or almost entirely in Go. And you just compile it to native code to make the node that you're going to run. You can download this build, you can download a Docker image, you can build it from source if you like to make sure that you have a correct build. But this runs in native code, and that means that the core engine runs at the speed of Geth. But not Geth that's throttled down like in Ethereum to have a very fast block execution time. The other thing that we do here, and we run that as the node, the other thing that we do here is we take just the state transition part of that and we compile that to WASM, using the same tool chain just with a different backend that generates WASM code instead of native code. We use that for proving. So if there is a dispute in the rollup protocol about what is a correct execution of the state transition function, we use the execution of the state transition function for one transaction. We dispute over that. That can be run in WASM, and you can do the standard optimistic rollup interactive dispute protocol over WASM execution. And so we use that for proving. And so that means that we get the benefits of using a compact, well-tested, well-engineered, and type-safe mechanism for expressing this program for use in proving. But if we were to run all of this on top of WASM, that there would be a slowdown that we don't want to pay. So for regular node execution, in the common case, you're running the native code. But if you need to prove, you are doing that over WASM. And we do some cross-checks to make sure that these things stay in sync as the protocol executes. Happy to talk about that part offline. So that's the basic design. This is the direction. This is where our stack is going. We think that Optimism is doing something not too different as they develop their current system. And I think this is the kind of direction that Rollup designs, at least in the optimistic case, are going to go. All right, let me talk now a bit about how we can scale something like this to the next zillion users. So the way to get to the largest scale essentially is to identify each dimension in which you can scale, and then scale as much as you can in that dimension, and make sure that those improvements will compose with each other. So this, this will have some things in common with what Dankrad said this morning. So what do we need? We need faster nodes so that each individual node can execute more transactions and beefier transactions on the same equipment. We need to increase the call data capacity because that is one of the bottlenecks for rollups of all sorts. We need to have more parallelism in the execution of each node so that even a single logically sequential EVM chain can be executed with more parallelism. And then finally, we need to do something to manage the storage bloat that will occur on a high-performance chain. Storage bloat is an issue for Ethereum. It will be a bigger issue for an Ethereum-compatible chain that's faster, because if you run n times faster, your storage, you'd expect, would grow n times as fast, and so you need to have a strategy for coping with that. So let me run through each of these and sort of talk about what we might do. Faster nodes, right, okay. So faster nodes, well, this is really about engineering the core node functionality. We are using Geth today because we think Geth is the best combination of reliability, strongly supported team, adherence to the Ethereum standard, including the common law parts of the standard, and and security. We need to move either to making Geth faster or to being able to switch to other node architectures which are faster. This is a really important thing. There are things architecturally that are in the pipeline for Ethereum which will allow nodes to operate faster. Things like changing the state tree representation to use something that is more optimized for fast execution and so on. So this is mostly a matter of engineering. Okay, more call data capacity. There's a lot that can be done here. The thing I want to highlight is the EIP 4844 blobs proposal, the so-called proto-dunk sharding, followed by full-on dunk sharding. We can't wait for those things to happen. They will be huge benefits for our user community and for all of the users of L2s. In the meantime, we have announced a version of the Nitro technology called AnyTrust, in which if you're willing to make a mild additional assumption about trust, we can move data availability off-chain, and therefore we can give you essentially the equivalent of, as if EIP 4844 existed already, we can give you that level of efficiency in exchange for a small security assumption. And so that's what we're doing in the shorter run. In the medium run, it is proto-dunk sharding, and in the long run, dunk sharding is going to be our answer here. Dunk sharding not only, as Dunkrod explained, I think very nicely this morning, lets you, will drive down the cost by driving up the capacity of the Ethereum chain to provide data availability, but it also is naturally scalable in a way over time that will allow us to continue to grow. One thing that's important, though, about those technologies is that they will not provide the kind of sequencer functionality that we think rollups need. So although those technologies will provide data availability is key because of that stage of settling, of recording the compressed batches onto the L1. That'll make that much cheaper and higher capacity, but we think a sequencer function will still be needed. All right, that's how we think about scaling up call data. We think that is a problem which is solved in principle. It's a matter of engineering and of building consensus to actually roll that out. I want to talk a little bit about storage bloat. This is a real issue, and if we're not careful, this could be the biggest barrier to scaling any of these systems, right? In the EVM model, storage is forever. The chain state grows and grows and grows. If your chain goes faster, your state grows faster. And so if you want to scale to 1 or 2 orders of magnitude above what Ethereum can do, you can expect 1 to 2 orders of magnitude the amount of state bloat or rate of state bloat that Ethereum has unless you do something. So eventually, you get to the point where your nodes can't store it all at reasonable cost. So you need to have some way of coping with that. And I think there are several strategies that are possible. One of them is to adopt or ideally accelerate some of the things that Ethereum is, the Ethereum research community is working on. Things like storage expiration. That's probably coming to Ethereum at some point. It might come to rollups sooner because of more storage bloat pressure. But those sorts of approaches, so storage is no longer forever. Storage is recoverable forever, but doesn't have to be held by every node forever. More efficient representations of data to make sure that you don't store data redundantly when you don't need to. That's going to help you up to a point. But eventually, I think everyone is going to get to the point where we're going to have to talk about sustainable pricing for storage. I'm giving a talk at the ETHconomics conference on either here or at the other venue on Thursday. I'll talk about this in a lot more detail, talk about specific proposals. But basically, if you have a problem that users or developers are using too much of something and it's not sustainable, you know, the standard approach is to think in terms of pricing. How can we generate economics that incent people just enough to be judicious in their use of storage and to be judicious about growing the storage? I think we're going to be forced, I think we're all in this sector going to be forced to do something like this. And so I think it's valuable to have a conversation as soon as we can about how sustainable pricing will work. But ultimately, we're going to need to price storage growth into the cost of transactions. And if we're not careful, that may become a major component and something, therefore, that application developers will be incented to strongly optimize for. And then finally, the last piece is more parallelism in the execution of a single logically sequential chain. And this ultimately means running transactions in parallel. Of course, you can only do that if they're independent and non-interfering. There's a bunch of proposals to try to surface that information more effectively to execution engines so that they can sort of deconflict and figure out a parallel scheduling strategy. But even if that's not available, you need to think in terms of what in the database world is called optimistic concurrency control, which basically means try to run things in parallel, and if they generate a conflict, kill the one that's logically later and retry it. And so there's various approaches here, but we need to try to push to increasing the parallelism on a single chain. Then we need to figure out how we can do effective sharding. Because no matter how much we grow the capacity of any one rollup chain, it's not going to be enough to meet the demand that the world would like to put on us. And so we need to figure out how we can operate effectively, efficiently, and in a relatively friction-free way in a world where we have multiple chains or multiple shards or L3s on top of L2s, branching out to L4s. You can imagine different kinds of approaches. The key to making all of that work is understanding how to do bridging and composability or bridging and interoperability in a way that is efficient, that doesn't sacrifice security, and that is reasonable for developers to use. That requires a lot of sophisticated thinking about trust models, and we're also really interested in that. We are interested, we have several team members here. I and my colleagues are really interested in talking to any of you about ideas around how to do this. One of the reasons to come here and one of the reasons to give this kind of talk is to try to foster a conversation within the community. And so I really do hope that happens. And in that spirit, I have about 3 minutes left for questions. Oh. Mandatory, everyone trying to hire everyone. Thank you. Any questions? Raise your hand. Over here.
So regarding the storage of the extra data with the transactions, I know there's networks out there who try to provide services as decentralized storage. Mm-hmm. I know you've thought about it.
Yeah.
Can you elaborate more? Like, what are the implications of integrated with Swarm, you know, or IPFS?
There's different approaches there. What we need, I think, for something like that to be effective, we would ask a bunch of questions about any system like that. One is, what are the security assumptions, obviously? Another one is, and to what extent does that solution provide durability of the data over time? Second, we would ask about latency. How quickly can you get a guarantee of availability? Number one. And number two, can you get a guarantee of availability that is verifiable on-chain, on the Ethereum chain, right? Because ultimately, if there is a dispute, we would need to be able to, someone would need to be able to substantiate that that data has been promised to be available, right? Because we can't admit data into the sequencer's queue. We can't accept external data availability as a substitute for on-chain availability unless we have a guarantee of availability, which we can check on-chain, that's available with reasonable latency and that doesn't have unacceptable security risks for our community. So that's how we would look at any proposal like that. Thanks. Right behind you.
Okay, so
this is the last question, I'm afraid.
Okay. So you mentioned that you want to decentralize the sequencers.
Yes.
In a way that you still have finality under Ethereum block time.
Yes.
And my question is, how are you planning to achieve this?
Yeah, so there is a research literature on this, and let me give you a very quick sketch. I'd be happy to dig into more detail. The basic idea is that instead of having a single sequencer, you have a committee of sequencers. And you can provide a guarantee that provided that a suitable supermajority of those are honest, then if Alice's transaction arrives at enough of them before Bob's transaction, then Alice's transaction will be before Bob's in the sequence. One way of visualizing that is to imagine that each of those sequencers publishes its claimed sequence, which is its claim about in what order, which transactions it received and in which order. And then you have a merging algorithm which you can run on top of BFT consensus between those sequencers, which guarantees to produce a fair merge result. I had to lie a tiny bit about what the guarantee is, but I'd be happy to nerd out on that with anybody afterward. But that's the basic picture. Committee, if sufficiently many of them are honest, then you'll give a guarantee of, you give an appropriate first come, first served guarantee. Thanks.